Hello, this is going to be a departure from my usual subjects that I do on advanced mathematics, set theory, philosophy. I'm going to do something that's targeted to geometry students, those of you in elementary school, middle school, high school, or even college who are taking uh, Euclidean geometry. We're going to discuss the law of sines, and I'm going to pose a challenge to you. And this challenge will be in the form of the best response video on the subject that I'm proposing. Those of you who are 18 and those of you who are still in high school, middle school, or elementary school, you're going to need to have your parents in the video with you, just so that there's permission given to do this. But if I will then choose, I will then choose the best response video on the subject that I give. I'll upload it as part of my videos. So this is mainly geared to young people, this challenge. If you're in college, you're taking geometry, let me know. Okay, but this is geared to geometry students who are young people. Again, if you will need to, for those of you who are 18 and under, you will need to have, or in high school and middle school and elementary school, you'll need to have your parents in the video there just to signal permission. So, okay, a teacher could probably work also, but I would actually prefer parents. If it's obviously inside of a classroom, that a teacher could possibly work, but parents preferred. Okay, law of sines. We're going to discuss the law of sines. The law of sines states that if you have a triangle and all three angles in the triangle are inscribed in the triangle, you have a situation where the sine of a given angle over the length of the side opposite is the same for all three angles. So we can see here the sine of A over EG is the same, and I'm using the absolute value sign. Really, I should use two lines and not one to make it more accurate, but we'll leave it as one for this video. Is the sine of A over EG is equal to the sine of C over EF is equal to the sine of B over FG. Okay, and I can also derive a bunch of different equations from that. And notice I have one circled that states that sine of A over sine of C is equal to EG over EF. Okay, so the sine of A divided by the sine of C is equal to length of EG over the length of EF. Now that can be derived algebraically from what we have here. I'm going to prove it, not in formal geometry. Okay, that's going to be your job next video, but I'm going to prove it using algebra. First of all, what is a sine? Here we go. Here's the relationship of a sine. Bottom line is a sine assumes that the sine of the angle assumes that I have a right triangle. Okay, so if I have the sine of this angle here, theta, it's going to assume a relationship of A, B, and C such that I have a right triangle inscribed. So those of you who haven't learned about it yet, you'll learn about it in the years ahead. Those of you who have, you've already learned about it, so I'm not going to dwell on it. The bottom line is that the sine of this angle theta is going to be the side opposite divided by the hypotenuse. Okay, so the sine of this angle theta is A, which is the line segment opposite of theta, divided by C, which is the hypotenuse of our inscribed right triangle. Okay, so bottom line, it's A over C, or opposite over hypotenuse. All right, so knowing that, we now have our familiar triangle that we had here, albeit I'm going to modify it just a little bit because we're allowed to do that, because it's supposed to be true for any triangle. And we're going to consider angles A and C, okay? I'm going to take point E, and I'm going to have a line that cuts right through angle B, and that it doesn't bisect, but it forms a right angle with EP is going to form a right angle with FG, okay, or two right angles, really. So what I now have is I've gone from one big triangle, FE, FEG, to two right triangles that share a common side. Okay, triangle EPF and then triangle EPG, and they share this common dotted line here, which also happens to be the angle opposite of both A and C. In other words, I can plug, this is going to be good, okay? I can plug line segment EP into my consideration of both sine A and sine C. Now, what is the sine of angle A? I should have a little angle signal for A there, but we'll worry about it for now. Okay, the sine of angle A is going to be EP, which is the side opposite, over EF, which is the hypotenuse. Okay, so it's going to be opposite over hypotenuse. EP over EF. Okay, and the sine of C is going to be EP over EG. Okay, because now I have C, it's going to be the angle opposite over the hypotenuse. So, voila, what do I have here? I have sine A is equal to EP over EF, and then sine C is equal to EP over EG. Well, I'm going to do some fancy algebra here. This isn't technically the best notation, but it's the clearest. Okay, so for your homework, don't use notation like this, but for this video, it'll be okay. All right. EP sine of angle A over sine of angle C is equal to EP over EF all together divided by EP over EG. Okay, so it's going to be this fraction here, EP over EF, okay, this ratio of this divided by this, all together, that whole thing divided by this ratio, EP over EG, okay? Well, what do I know about dividing by a fraction or a mixed number? What I know about it is it's the same thing as multiplying by its inverse, right? So if I take EP over EF and divide it by EP over EG, it's the same thing as multiplying by EG over EP, which is fortunate because the EP's cancel, and I'm now left with sine of angle A over sine of angle C is equal to EG over here divided by EF, okay? Or sine of angle C over sine of angle A over sine of angle C is equal to the length of EG divided by the length of EF. Now, what do I can use that to derive this algebraic formula here. Sine A over EG is equal to sine C over EF. Well, notice that sine of angle A over EG, in other words, sine of angle A over this line opposite from A, is the same as sine of angle C over this line opposite from C. Now, I could easily draw I could easily shuffle. I could take A and I could note this as A. I could take C and I could note this. And let me put it this way: I could easily take our labels of angles and rotate them. Right? I could easily make this over here, let's say angle C, and then this over here angle A, and then this over here angle B. Right? So bottom line is, if I've proven the law of sines for two angles, I've proven the law of sines for any two angles. Now this is the proof that now what about for angles that would be obtuse? Remember that the sine of, let's say, 120 degrees is the same thing as the sine of 60 degrees. So the sine of 135 degrees is the same thing as sine of 45 degrees. So bottom line is, if I prove it with, I'm using two acute angles here just to make it easier, but it would work for equivalent obtuse angles. Now, if you have your parents' permission, and it's okay, law of sines is affirmed. Now, get your parents' permission. I'm not going to accept just a teacher. You're going to need to have your parents for this. I need you to and I'll choose the best response video on this subject and upload it as one of my videos. I need you to prove for an angle, let's say an angle inscribed from the center of a circle to 2 points on the edge of a circle, or in the circumference of a circle, okay, with a symmetrical diameter going through it, bisecting that angle. We'll call it angle A. And let's go continue this in part 2.